Okay, so we're looking at section 4.2, the mean value theorem and increasing and decreasing functions. So let's take a look at this. The mean value theorem. Okay, mean value theorem says if a function is continuous on the closed interval from A to B and differentiable on the open interval from A to B, then there exists at least one point in that open interval where the derivative at that point will be equal to the secant slope of the interval. Okay, this is important. It's kind of like what we were talking about when we were going traveling and stuff like that. So if you're going on a trip and it takes you 3 hours to go 150 miles, then you're basically going 50 miles per hour on average. Well, what that means is at some point along the trip, you had to have gone 50 miles an hour actually. And that's kind of what this is talking about. Your rate actually had to equal the average of your trip. And so this graphically kind of looks like this. So let's take a look at it real quick. Okay, so here is from A to B. I have some function in here. This is the secant slope right there, the average between A and B. And you'll notice that I have a slope that is parallel to that and a slope that is parallel to that. And so therefore you see that we have two values in this example where the derivative at that point, the slope of the tangent line, is equal to the slope of the secant line. There's at least one point C in the interval, at least one, there could be more, where the tangent line of the graph of F is parallel to the segment with the endpoints A and B. So basically the secant slope. Okay? So again, another way to look at it right here, a function that is well behaved, continuous on the closed interval, differentiable on the open interval, then there has a property that the instantaneous rate of change of the function somewhere in the interval is equal to the average rate of change over the interval. So that's basically what we're talking about. So a real quick example right here. That's what I kind of laid out for you already. If she drives 150 miles, okay, and she leaves at noon, arrives at 3, what is the average rate of change of her distance traveled in miles per hour? What does the MVT, the mean value theorem, tell us about her trip? And that she drove 150 miles in 3 hours, so the average rate of change is 50 miles per hour. The mean value theorem tells us that there must have been at least one moment in that time between noon and 3 where she was actually traveling 50 miles per hour. That's kind of like a real world example of the mean value theorem occurring. Okay, and so let's take a look at some stuff right here. We're going to explore the mean value theorem in a little bit more detail. So let's take a look at some stuff. Relaxing the hypothesis. What could happen if the function is continuous on the closed interval but not differentiable on the open interval? Okay, so the thing about mean value theorem is this. You have to establish the conditions first. Before I can talk about this, I have to show that the function is continuous on a closed interval and differentiable on the open interval. Then I can talk about this, meaning that it does exist. The mean value theorem is an existence theorem. It's telling you that it will exist a number. So what happens if I don't have all of that in the front? What if it's continuous but not differentiable? Remember, differentiable means that there is at least one point. Not differentiable means that there is at least one point where the derivative fails to exist. If we relax the hypothesis of the theorem, the conclusion could still be true, but it doesn't have to be true. If both conditions are met, continuous on the closed, differentiable on the open, then there exists. This one is a guarantee. But if I relax this hypothesis, this is no longer a guarantee. It could happen, but it doesn't have to happen. And so we're going to look at some examples about this so you can kind of see how this lays out and so forth. So here is our first example that we're going to walk through together. So let's start with that one up here at the top. Let me get it lined up here so you can see it. So we have a graph over here. Okay, the graph of function f. F is continuous on the interval from 0 to 4. but it is not differentiable at 2 because we have a corner up here. Is there a point on this interval such that the derivative at C is going to be equal to this slope? Well, the slope, as you can see from here, I kind of laid it out, is going to be 0. Is it possible that's going to happen? So look at it. If you look at all the tangent lines to this curve, do I have any of them that's going to be parallel to this one? All of these little tangent lines here are never going to be parallel to it because that point up here, which is where it would have happened, doesn't exist. So the answer to this is no, it's not possible for that to occur. So this is an example where if it's not differentiable, see, this didn't even occur. Let's look at another example. This time I'm asking you to graph. We're going to graph a function that is continuous on the closed interval, but fails to be differentiable on the open interval. Yet despite this, there is a point where this occurs. Okay? So as you think about these things, remember, we've got to have a point of non-differentiability that occurs at breaks and gaps, not gaps, but corners and cusps and things like that. So we might want to include one of those things in our picture. So let's go ahead and take a shot at this one here. I'm going to show you what I come up with. Remember, there are many different ways to draw this. It doesn't have to be this way. But if I draw a curve that looks like this, I'm going to start here at 0. We're going to end at 4. It doesn't matter. I can do A and B. Let's do A and B. So then I'm going to put a dot here, and this is where I'm going to end up here. So this one can come up like this, and I can do a corner or a cusp, and then I can come around and do that right there. Okay, so the secant slope, the average, is this dotted line. Oop, I missed it. You see the point? There it is, the dotted line. Do I have a point where it would be parallel? Is there some point on the curve that is parallel to this? And yeah, I can find one right about there. So this here would be point C. Okay, so I can have it. It can occur, okay, where it's not differentiable in the open interval, but it still applies. I can still find something. But remember, the mean value theorem is in existence. It guarantees the existence of something. This was not guaranteed, as you can see. Okay, let's look at another example here. We're going to graph another function. Graph a function that is differentiable on the open interval, but fails to be continuous on the closed interval. Is that even possible? What would it look like? What would it mean? Because why do I even have to have this question? Well, because differentiability implies continuity. Okay? If a function is differentiable, that means it has to be continuous. But I'm only differentiable on the open interval. How would I fail to be continuous on the closed? Well, it would have to be discontinuous at an endpoint. Okay? So it has to be discontinuous at an endpoint. So what would that look like? Can I do that? Well, again, I can draw some kind of curve. And what I need to do, if this is A and this is B over here, then at one of these endpoints, okay, I need to have like an open circle. And then I can do what? Then I can come down here and have some kind of curve that does this, just for the sake of argument. But over here, I can put a dot. So what I have is that's my secant slope right there. And can I find a line, a point where the tangent line would be parallel to that? That's somewhere right about there. So it's discontinuous at this point, at an endpoint, but yet I could still find one. So it is possible for that to occur. Okay. Graph a function that is differentiable on the open interval but fails to be continuous on the closed interval, but there is no point where this happens. This is one where it did happen. Is there any way I can find one where it doesn't happen? Can I come up with an example for that? Okay, so remember, I have to be able to find no tangent line that is parallel to the secant slope. So when you think about it, again, there's a lot of different ones you can do, but I need a secant slope. I can have a point that's not, it's differentiable but not continuous, so we're at an endpoint again. So at some endpoint, okay, I can do this again where I can split it like that. It doesn't have to be here. It can be on the other end. And then I have to have some kind of point over here for my B. And so this is the curve, but this is the secant slope. You can see that there is no way I can find any kind of tangent line that is going to be parallel to this. See, I have to go this way, and there's no way I can find that point. So this would be an example of this one, where it is differentiable on the open but fails to be continuous. And there is no point C where this occurs. Okay? So let me put this up here so I have some side notes and stuff that you might be useful to see on these notes over here. So particularly this one right here, I didn't write all those little side notes down there. So just take a moment, pause, and copy that. And then down at the bottom here, some closing arguments on this part right here before we do more examples. The mean value theorem is tested mainly in a graphical or table form on the test. When answering a free response questions, if you're going to state a theorem or in your justification, so if you're going to use the mean value theorem as a justification for your answer, you must state and show that the hypothesis conditions are met. The whole point of this is you can't use the mean value theorem until you have shown that it is a continuous function on the closed interval and differentiable on the open interval in some way. Okay, so let's take a look at some other examples as we move along. So here's another example we have right here that you might see on a test. Selected values of a differentiable function f are given in this table. What is the fewest possible number of values of c in this interval for which the mean value theorem guarantees that the derivative at c is equal to 6? Okay, so let's talk about what all this means. First things first, we have a differentiable function f. Okay, if f is differentiable on an interval, then it is continuous on that interval. Okay, so remember, it's continuous on the closed, but differentiable on the open. So I can come over here and I can say, since f is differentiable, then it is continuous on 1/9, because it's differentiable on the open interval. So I now know it's continuous on the open interval. Okay, we're looking in here. Is there a point in here, right, where we can get 6? So this is why we don't need to look at the endpoints here. There's no way I can get a 6 from the endpoints. Okay, so it's going to occur inside the interior somewhere. So based off of that, so by the mean value theorem, there must be a C somewhere. And because there might be more than one, I'm going to call this first one C1. So can I find it somewhere? Can I find a secant slope somewhere that is equal to 6? See, that's what I'm doing. Is there going to be one? I got to find the 6. So if I look around here, I can see that I have one right between these two. Take a look at this slope here. This right here is a plus 12. This is a plus 2. 12 over 2 is 6. So the answer is yes. There is some C value where f prime of C is C1 is equal to f of 5 minus f of 3 over 5 minus 3. There's 18, 6 over 2, which is 6. But is there another one? Can I find another one somewhere? So we look around Now, you don't have to do side to side of each other. Look beyond. This one does not produce one. But if you look closely, you'll see that from 5 to 9 does. Okay? And so I can come over here and say that there's another one. Also, by the mean value theorem, there is another C, we'll call C2, in this interval from 5 to 9, where f prime of C2 is equal to f of 9 minus f of 5 over 9 minus 5. So we're going to have a 4 on the bottom. We have 42 minus 18, and that reduces down to a 6. So what is the fewest number of values that we can do? There are 2 of them. Okay? There are 2 values that we have found, and there's my reasons why. Let's look at another application. What is the rate? The rate at which water flows out of a pipe in gallons per hour is given by this differentiable function, R of T. T is measured in hours. The table shows the rate as measured every 3 hours for a 24-hour period. Is there some value T? Is there a time between 0 and 24 such that the instantaneous rate of change for R is equal to 0? So here's the thing to keep in mind. Even though R is itself a rate, which means it's a derivative of some other function, I can still talk about this as a regular function, and so I need to do the derivative of that function. Okay? So just remember that. Derivatives are just of a function, so you can actually answer all questions based off of a derivative, no matter where the starting function is at. So do I have one? Well, if I have a rate of 0, what they're asking here is there a t, some value in this interval, where the secant slope is 0? Okay, is that even possible? Well, first off, I have a differential equation, correct? It's differentiable. Okay, and so what do I know? Well, since R of t is a differentiable function, okay, then R of t is continuous on this interval. So why? Why can I say that? Okay, because R is a differentiable function. Okay, does the water go in the pipe beyond this time frame? Yes. Okay, so since it's differentiable beyond the scope of this little window we're looking at, okay, then the function is continuous in that same locations. So it definitely is continuous on this closed interval right from here to here. That's how I can make my justification here for yourself, so you know. So it's continuous to this, and also because, if you look closely, notice I have the same rate here, same output, don't I? That gives us the 0. Because R of 24 minus R at 0, 24 minus 0, is equal to 9.6 minus 9.6 over 24, which is irrelevant because this is equal to 0. So I now have the secant slope as 0. Because I have a differentiable function and continuous on the closed interval, and I have this secant slope is equal to 0, I can say by the mean value theorem, there is a value of t between 0 and 24, where R prime of t must be equal to 0. And that's how you can answer that question. Okay? So there's 2 examples right there that we looked at. Let's go look at some other stuff. That's the mean value theorem. We will explore this in more detail later on and do other examples of the types that you will be seeing. But we're going to look at the other half of this assignment, which is increasing and decreasing functions. So let me pull that up so you can read it. increasing and decreasing. Now, we had a cursory idea of what increasing is, and here it is now formalized. Here's the definition. Let f be a function defined on some interval, and x1 and x2 be any numbers in that interval. A function is increasing on the interval, and they're ordering x1 and x2. So x1 is smaller than x2. So take the two numbers. Means if this is smaller than that, then f of x1 must be smaller than f of x2. That means that we are increasing. The y values are going up. Decreasing is the y values will be going down. The next y value is smaller than the previous y value. Based off the, because of the mean value theorem, we can identify this where graphs fall and rise from this concept. Okay, and this is how we're going to be looking at this. Let f be continuous on the closed interval and differentiable on the open interval. If f prime of x, if the derivative of x is positive on the interval, then I can say that the function is increasing on this closed interval. If I find that the derivative is negative on the interval, then I can say that f is decreasing on this interval. And so this is our increasing, decreasing functions that you're going to be asked to do. Okay, it goes through a process I'm going to show you here right now on some examples to show you how you're going to use this to our advantage. Okay, so let me go ahead and flip over to our example. And we'll start with this one right here. So the derivative of a function f is given by that formula right there. On what interval or intervals is f of x increasing? Okay, so what do I need to know? So it's important to know, what is it is what we're talking about. So I'm talking about increasing. So what do I need to know to show that f is increasing? Well, from the previous page, we need to know when f prime of x is greater than 0. So I need to find, to separate from positive and negative, I got to find out where it is 0. So when is f prime of x equal to 0? Okay, so we go and find the derivative, which is right here. So f prime of x equals 3x squared minus 12x. I want that to equal 0. We factor this stuff out. We solve this out, so I get x equals 0 or x equals 4. So I have two locations. We then go and make a number line. It doesn't have to be big. Put those 2 points in there because those are where the derivative is 0. Remember, those are called critical points. Put them in your table as a reference. This is where it is 0. And then we need to do a test here, this region, for the first derivative, and determine which regions are positive and which regions are negative. So you simply pick an arbitrary point in this region over here. You plug it in and see if you get a positive or negative value. So if I test the point over here and I plug it in, if I plug in like -5, this right here will be negative. This right here would be negative. Negative times a negative is positive. Pick a number between 0 and 4. 1, this will be positive. This will be negative. My answer will be negative. And if I pick another number over here like 5, everything is positive. And so I have that right there. This is your test points. Okay? What do I do now? Well, these regions that are positive, because I wanted to find out where it's positive, are where this function f is increasing. So I can write my answer now. So my answer is going to be f is increasing on the intervals from -infinity to 0 and from 4 to infinity, because everything has to have a reason. F prime of x is greater than or equal to 0 on these intervals. And there you go. That is your answer. Okay? And remember, for increasing or decreasing, the endpoints are included. Let's look at another example. This is where I give you information as a graph. The graph of the derivative is shown on what interval or intervals is f of x increasing. Okay, so in a graph situation, if this over here is my derivative, this is f prime of x. Always look at the picture and see what you actually have and what they're asking you. So again, what do I need to know? I need to know, to show increasing, I need to know when the derivative is positive. When is f prime of x greater than 0? That's what I'm looking for. Well, in a graph situation, we know what? If the graph is above the x-axis, that's positive. If the graph is below the x-axis, that's negative. And so you can see then that we have the same answers we had above. Okay? The same answer written the same way. The function f is increasing on the intervals from negative infinity to 0 and from 4 to infinity because f prime of x is greater than or equal to 0. There. Is 0 and above, 0 and above. Okay? Here it is in a table format. The function f is differentiable for all real numbers. Okay, that means it's also continuous for all real numbers. And its derivative has exactly 2 zeros. Selected values of the derivative are shown in the table. So this is f prime. Sorry. Forgot to write that down. What are the intervals of x where f of x is increasing? Well, since they told me I have exactly 2 zeros, and I can see the 2 zeros in here, you can see clearly that that's my boundary points, kind of like my number line up here. And so I can see that the y values are positive over here, but negative in between. It's kind of the same thing again. And so then I can tell that my answer is going to be exactly the same because this is how I wrote it. The function f is increasing on the intervals from negative infinity to 0 and from 4 to infinity because f prime of x is greater than or equal to 0 there. And there you go. So pay attention to this. Little side note here I'm going to give you real quick. I'm going to move this over so you can read everything that I wrote in my original notes. Let's take a look. And I'll pause it for each one of these things so you can take a moment here and get the little side notes that I wrote. So I'll go ahead and pause here. Okay, I'm going to slide it up. And you can pause here. All right. Now, here's a little side note for this table up here from this thing here. If the table looks like this, if you look at it closely here, see how it's got a 0 right here. This is positive. This is negative, and then it went positive again. Okay? Because we don't know where that 0 lies between these two things. I don't know where it is. We cannot determine the intervals. We need to know where the derivative is equal to 0 or undefined to make the conclusions that we did up above. I only have the 1 here. I can't make it. I don't know where it is here. So I can't find that second interval. And so I have to know where the zeros are, okay, or where it's undefined in that little space between these two things right here. So that's kind of important to keep an eye out for, okay? The next thing we have here, I got a couple more things and then one more example. So this is like a little sentence frame to help you write out your answers when you do these problems. The function is increasing or decreasing on this interval because of this reason here, or decreasing for this reason here. So you can use either one of these two symbols. It should be still fine. Don't say that f prime of x is positive there, because that's not possible. That's not necessarily true, because if the derivative was 0 in that interval, then you're going to be marked incorrect. Okay, so don't say positive means not 0. 0 is not included in a positive statement. Okay, So say it in this fashion over here, okay? And so we have one more example down here. And I'll just flip this over here so we can do it. So here's our problem. Here's a function f. The derivative of f is given. There's that derivative. Oh, that's a beautiful one. All that mess right there is the derivative. On what interval or intervals is this function increasing? So what do I need to know? I need to know when f prime of x is equal to 0. Okay? So here's f prime of x. I'm not going to write it all again, but each of these is a product. So it's already factored. So I need to know when is the sine of x plus 3 equal to 0. I need to know when x squared equals 0, when e to the x minus 1 equals 0, and when 5 minus x equals 0. And I got to look at each one of these individual things and see if it's even possible. Okay, so remember the sine of x, if you think of the graph itself, it goes from -1 to 1. So this thing here is always going to be positive. So this right here, the sine of x plus 3 is always greater than 0. It can't be equal to 0 for all x, so there is no 0 from this. When is x squared equal to 0? Well, when x equals 0. So we have that one. E to x minus 1, when is that going to be 0? Well, when that quantity is a 1, which means x equals 0. And when is this going to be 0? Well, when x equals 5. So once I have that, okay, or where f of x is, or where f prime of x is undefined, which is not in any one of those situations, then I do my number line based off of these zeros. Here's 0, here's 5. It doesn't have to be written any accurately. I put the derivative out here because I'm testing the derivative for positive and negative. Okay, and we can go through here and test each one of these numbers. So you pick a number from each region, you test it in this up here, determine if it's positive or negative. Okay, this is going to be null and void. This is always going to be positive. We said that's always greater than 0. Squared is always bigger than 0. Okay, e to the x minus 1. All right, so we basically lowered it 1 unit, so there's a possibility that it might be negative in there. And this over here might be negative. So let's take a look at some test points. I'll let you confirm this on your own, but here's what I came up with for the sake of time in this video. I got that right there. Okay, so from that I can draw my conclusion, which is f of x is increasing on the interval from 0 to 5 because f prime of x is greater than or equal to 0 there. And there you go. All right. So that right there is the end of this video. We'll do more problems together in class.